So to start off, what your chapter 7 is going to be about is haloalkanes. Okay, so halogens and alkanes. Alkanes are typically unreactive. You don't have any polarity associated with them, which is why they don't react. Okay, and this is where that chapter 7 comes in. So it's first starting to transition from looking at structures to now looking at reactivity. Can you build something? Okay, so there's a brief little bit on nomenclature here, so you've got that information if you needed it, and then back to the reactivity. Okay, halogens are typically more electronegative than your carbon, so they're going to draw electron density away from that carbon. That means that carbon becomes fairly positive, and the halogens become partially negative. Okay? This generates some reactivity. That reactivity is what we're going to take advantage of when we look at substitution reactions. Come on now. Some other kind of pseudo-nomenclature things that you need to be aware of in case you haven't already heard of these terms. Primary, secondary, tertiary. You guys heard that, understand it, believe it? Okay, I'm going to trust that you understand those and just move on. So as far as the reactions that you're going to do in class, you're going to run two different types. So the whole goal of this lab is to get you to figure out and learn or self-discover the different mechanisms for substitution and what things control those mechanisms. So we're not going to tell you a whole lot about the application part of it. A lot of those kind of subtle rules are things that you're going to develop. Okay? So in the SN1 class, you're going to take some kind of alkyl chloride, so some carbon-containing structure that also has a chlorine, and you're going to mix that with ethanol as your solvent and silver nitrate. A reaction is going to occur where you're going to do a substitution. The ethanol will swap out for the chlorine. You end up with a new product. Okay? All of that is colorless. You can't see anything. Okay? The whole goal is to see and track your reaction. Well, if you can't see it, that makes it very difficult to track. Okay? So one of the things that we're going to visualize is silver chloride precipitate. So if you see a solid, that means that reaction worked, okay, for your SN1 situation. Okay, and that's why I'm trying to show that in kind of extra colors up there so you can kind of see it. Okay, so that's what you're visualizing, is that solid forming. In the SN2 case, we're going to change the reaction conditions. So the solvent changes and the reagents slightly change as well. Okay, and in that case, what we're going to do is a substitution between iodine and chlorine. Okay, so we're going to swap out the chloride for an iodide, and in the process, we're going to form sodium chloride. Okay, what is sodium chloride also commonly known as? Salt. What do you know about salt, or salts in general? Dissolves in water. So we started with an alkyl chloride, which was clear and colorless. We ended with an alkyl chloride that was clear and colorless. And we've got a salt, which we would expect to dissolve. What do we visualize? Nothing. That makes it, again, really, really difficult to figure out. Okay? The reason the sodium chloride is starred there is because we are visualizing the formation of sodium chloride. Okay? Salts are soluble in water. However, are we in water? We're in a different solvent. Okay? We're in acetone, which means we will be able to see that sodium chloride precipitate. Okay? So it's in both reactions you'll be looking for that white precipitate. Couple issues that are going to show up with this. Okay? In the SN1 reaction, we get a false positive. Okay? It does not test for the alkyl halide reaction. What it tests for is the presence of chloride ion. So if there's chloride present, the silver reacts with it and forms a solid. Okay? Where might we find chloride ion? Good call. Salt. Sodium chloride. Salt water. Our general water supply. Okay? So one of the big problems that we get with that SN1 reaction is a lot of false positives. You might see a precipitate due to impurities or some other contamination. Okay? So that makes that SN1 reaction a little bit more difficult for the reason of false positives. When we move to the SN2, we already discussed the issue with our product there, our precipitate, the sodium chloride. It's soluble in water. What happens if there's water present? It dissolves, and you don't see anything. So even though you produced the product, you think it's a negative result because you can't see that. Okay? So that's the things that make these two reactions, or this entire experiment, kind of tricky. Okay? You get the false positives from the SN1, and you get the false negatives from the SN2. Okay? We can't really control the SN1 unless we just limit what things come into it. Okay? Which means you should only be using the reagents given to you. If you start mixing in a little bit of water, you could be contaminating your sample with chloride. For the SN2, if you start mixing in a little bit of water, what happens to the solubility of the sodium chloride? It increases and it dissolves. Okay? So you've got to be very, very careful with your glassware. Make sure it's clean and dry as best as possible. Otherwise, you could end up getting false results. Okay? The other thing that we're going to do is summarize the results at the end of class. Okay? So as far as the experimental procedure goes, it's really straightforward. It's something that can get done in a matter of minutes. Okay? It's prolonged because everybody has to fight for the same bottle of chemicals, okay, which makes it a little bit more difficult. But then we're also going to prolong it because of these false results, which means what you're going to end up doing is collect all of your data, summarize your results on the board. Okay, so we'll have a nice little table set up where you can put in, yes, I got a positive result or not. And then at the end of class, or once all the groups have compiled all their data, Stephanie or Robin will go through the data with you and kind of wash out any of the false results. Okay, does that make sense? If you try to do this experiment based solely on your results, it better be the correct results that you're getting. Okay, and that can be problematic. So what we're going to do is start to address what's happening with this reaction. Okay, so if we take a look at a simple substitution example, okay, every problem that you should be seeing from here on out is going to be falling under the same kind of category. You should be trying to look through and identify bonds that are broken and bonds that are formed. If you can find those bonds, everything else is irrelevant, so ignore it. Okay? So if you look at this example, what bonds were broken? Is there any bond broken? Okay, yes. Which bond broke? Okay, we've got a carbon iodide bond that broke. Anything else broke? Okay, we got now an NCl bond broke. Anything form? Okay, we've got a carbon-chlorine bond that formed, and we also formed that sodium iodine bond. Okay? The trick behind these substitution reactions is some chemist came along, looked at it, totaled these things all up, and then started to make some assumptions and simplifications. How strong is an ionic bond? For instance, if I put it in water, does it stay a bond? When I add sodium chloride to water, what's the first thing it does? It dissolves into the water or into its ions. Did that bond stay there? No. So how strong is that bond? Relatively weak. So what we're going to do is assume that those interactions are fairly minor. So we'll exclude those interactions from our discussion. And now what we're going to look at is just the breaking of the carbon-iodine bond and the formation of the carbon-chlorine bond. So we only have two things now. All we've got to do is look at all the possible orders or the possible sequences that these things can be done in. Okay? Which may seem like a lot, but you only end up with three possible ways. One of those ways you could immediately eliminate, which we won't discuss. I'll leave you to figure that one out. Okay? So we'll look at what we would refer to as the SN1 reaction. We're going to break the carbon-iodine bond first, then we're going to form the carbon-chlorine. Okay, I think I had butane. Let's go back. So if we start, okay, I don't remember what I had. What did I have? Propane. We'll go ahead and start with our propane. The first step says to break the carbon-iodine bond. Okay, how could we break that? What is that bond? What does that line represent? A bond. What's in a bond? Electrons. Where are those electrons spending most of their time? Why on the iodine? It's more electronegative. So now that I've got to force that bond apart, I'm going to break it. Where are those electrons going to go? Towards the iodine. So what we'll do is add a curved arrow with a two-headed arrow with the electrons going towards the iodine. Okay? That is all our step said to do, so let's go ahead and leave it at that and draw the product of that. What do we get? We get our carbon, we get our iodine. What happened to the iodine? It gained electrons, which means it has become negative. What happened to the carbon? Lost electrons, so it's now positive. Okay? What else happens to be floating around in solution? Say, perhaps in our next step. Chlorine. So let's go ahead and draw on our chloride from our sodium chloride. Also happens to be negative. Okay? I want to form the bond, so what should I do? Okay, right idea. I want to bond it to carbon. How would I show that? Let's draw an arrow from our electrons towards the positive. What I've shown now is the electron sharing. What's the result? We end up with our final product. Okay? So all we're trying to do is singularly describe everything that's occurring and stepwise moving through it. Okay? Kind of makes sense? What happens if, say, we switched it up, and now we're going to break the carbon-iodine bond at the exact same instant that we form the carbon-chlorine bond. So how could we show that? Well, there's our carbon-iodine bond. I need to break that bond. How can I show that? Good, the exact same way that we did before. We'll take the electrons out of the bond and we'll give it to the iodine. So we've now broken that bond, but it says I have to form the carbon-chlorine at the same time. How can I show the formation at the same time? I need to show another sequence of arrows showing the chloride coming in from the other direction. Okay. What's the result of this? The exact same product. I'm going to draw it a little bit goofy. I'm actually going to leave it to you guys to discover why, I think. We'll see. And we end up with our same products, just in a shorter reaction. Okay? Believe it or not, these two mechanisms determine the rest of that handout. It's critically evaluating each of these two steps and trying to figure out exactly what occurs, what things might help it, what things might hurt it. Okay? For instance, I showed the chlorine coming in behind the iodine, not directly on the same side. Any ideas why I might have done that? What is iodine leaving with? Electrons. What is the chloride coming in with? Electrons. What happens when I get those two electrons near each other? They repel away. Can the chloride come in from the same side that the iodine's on? No, because it's just going to repel away. So we've got to be able to put that chloride coming in as far away from the iodine as possible. Where's as far away as possible? The other side, also commonly referred to as the backside. Okay? So you'll typically hear backside attack in conjunction with SN2. Okay? So some of the things that you need to be familiar with, in theory you guys are already familiar with these, but just in case, you get your standard reaction definitions. If you can go through and identify in any given reaction these definitions, or at least one of them, that helps you out a lot. Because if you've identified one of them, what's it going to react with? The opposite. So if you found a Bronsted-Lowry acid, it's going to react with a base. So you should be able to predict and follow the chemistry if you know the definitions. Okay? When we're looking at Bronsted-Lowry, it's all about hydrogen ions. So it's a fairly narrow definition, but it works for acid-base chemistry. For most of the chemistry that you're going to see this semester, you're looking at the transfer of electrons. Hence, back when we looked at our mechanisms, we showed the red arrows to show the flow of, that's right, electrons. Okay? So your Lewis definition and then the nucleophile, electrophile, okay, both of those are pretty much the same thing. We just decided to come up with different names for them. Okay? And those are going to be the most relevant for you. I would highly recommend that you've got these memorized if you expect to make it through class. Okay? If you don't expect to make it through class, that's fine. Okay? One of the big things that we'll notice from the SN or the substitution reactions is it was SN. Any idea what N might stand for? That's right, nucleophiles. That's why it's on the top of this slide. Okay? So what we need to be able to do is identify a nucleophile for our reaction. If we don't have that nucleophile, we can't get the substitution reaction to occur. Okay? At least according to these mechanisms. So things that you need to look for and identify right away is it's going to have donatable electrons. There has to be electrons present. Okay? This means electrons in anything other than a sigma bond. Okay? So if you've got electrons in single bonds, you can't attack those or can't use those. Other big signals, it's typically negatively charged. The more negative it is, what does it have more of? Electrons. What was rule number 1? It has to have donatable electrons. So if it's negatively charged, it's more than likely going to have more electrons. Okay? The other thing that we'll look at is electronegativity. Okay? The lower electronegativity, typically the more nucleophilic, assuming the first two rules have been satisfied. Okay? Why might that be the case? Our nucleophile has to donate electrons, meaning it gives them up to another atom. Okay? If it's a highly electronegative element, does it want to donate those electrons? No. By definition, it wants the other direction. Okay? Those are your three primary rules for nucleophiles. If you can identify and rank compounds based on those three rules, you should be able to get through most of the class. The last two ones on there, 4 and 5, are a lot more difficult, usually require a lot more interpretation as well. I'm not going to read over those because those aren't going to be particularly relevant for, it's not quite true. Polar protic and polar aprotic. You're going to be looking at those solvents in this activity and trying to determine which one of those would be best for which mechanism or for each mechanism. Okay? Again, the handout I think does a decent job directing you in that direction, so I'll let you figure that out. And we're not looking at steric hindrance at all. One of the last things we'll evaluate is leaving group ability. Okay? We had to have an atom leave or take the electrons with it. Okay? If we looked at our general reaction, our very first step of, say, the SN1, we had our iodide, and what was the very first thing it did? It took the electrons with it. Why did I not try and do, say, a substitution on the hydrogen that is also there? Why does the hydrogen not take the electrons? True, but it could leave as H-. It could still very well hold those. So why would I have iodide leave as opposed to H-? Okay. Remember how we've talked about stability? Everything wants to be stable. Well, to be stable, it needs to be neutral. So we want to minimize the charge as much as possible. If we look at the size of hydride, hydrogen's pretty small. So there's our hydride, or H-. What's the size of iodide? There's our I-. Okay? It's a lot larger, meaning it can stabilize those electrons. Remember that whole electrical outlet argument that we had a little while ago? Which one would you rather stick your hand into? It's the same idea here. Iodide can minimize that negative charge. Okay? Where hydride localizes it to an individual point, meaning it is extremely reactive and unstable. A leaving group needs to be stable. So everything it's going to do is try to minimize that charge as best as possible. Okay? The other thing that we'll look at is in the SN1 reaction. Our very first step was the leaving group to leave. what it leaves behind is a positive charge. So not only do we need a leaving group, but we also have to make sure that the other product of that step is also relatively stable. Okay? So we could look at cation stability. Ignore the radical portion at the top. That's my fault. Okay? I like to go through and call it zeroary, primary, secondary, tertiary, because that just numerically makes sense. You'll probably hear it referred to as methyl. Okay? Why is it a tertiary cation? Because it's bonded to 3 different carbons. So you can take a look at each of those carbons. Which of those species is the most stable? Or which one's the most unstable? Tertiary is the most stable. Okay, why do you know that?
Because the poles are equal.
Poles are equal. I'm going to tell you right now, your zeroary has equal poles as well. What makes each of these unstable? Charge, the positive charge, right? How can I stabilize a positive charge? You need to give it something negative. What's the easiest thing that's negative that we can try and move around? Electrons. So what are we going to do in each of these cases? Look at the electrons near that cation. The closest source would be those bonds. Each of those bonds carries how many electrons? Less than 3, greater than 1. 2 electrons. Okay? 3 bonds, 2 electrons. We've got 6 electrons. Unfortunately, what's the difference between each of those? They all have 3 bonds, each with 2 electrons. So what do? We move one step further away. And what do we encounter if we move one step further away? We should look at an atom. Hydrogen versus carbon. What's the difference? Is there a difference? Carbon has more electrons because it's bigger. Okay? What does that mean for us? Well, if carbon brings in more electrons, we can go through and do an electron count. Okay? How many electrons do we want to say hydrogen brings in? Okay, 1. So if we look at the zeroary, how many electrons does total come in to stabilize that cation? 3. If we look at our primary, how many electrons are brought in? Carbon brings in how many? Okay, I'm not quite sure how we're going to count, but 6 works for me. We got 6 total electrons. Hydrogen brought in 1, so how many electrons do we have around that one? 8. What do we have around our secondary? 6 and 6 is 12, and 1, 13. And our tertiary? We've got 18. Which of those is going to be the most stable? The tertiary, because it has the most supporting electrons around that cation. We can't physically move them in, at least in this stage, but they can at least be close enough to help stabilize that. Okay? Which means when we look at the SN1 reaction, we need to form the cation. Most of our reactivity is going to center around tertiary and secondary cations, because those cations are stable. Okay? Whoops. We just mentioned the SN2, the backside attack. I'm just kind of including this so that you're aware of it. Okay? We just mentioned that it comes in from the backside. Because you're in this chapter now, can anybody tell me something special about this structure right here? What's special about that compound? Has a stereocenter, right? That carbon. It's a chiral carbon, a stereocenter, which means we're looking at stereochemistry. In the SN2 reaction, what we'll end up seeing is something referred to as inversion of stereochemistry. Okay? Again, I just want you to be aware of it. The handout has some questions on it because I think I left them off on there, but you also aren't graded on that portion of it because I don't think you'll get that far. Okay? This very last slide is looking at kind of a summary of each of these types of mechanisms. Okay? So if you're asked for particular substitution reactions, the things that are in bold are the things that I think are the most important. Things that are italicized or smaller font are still important, just not quite as important. And the things that are crossed out because I don't think you see them even in your lecture. Okay? So at this point, you should be able to go through and do that handout, the group activity. If you've got any questions about it, please raise your hand, and Stephanie or I will be right there to help you out.